Alright, welcome back. This is Chapter 3 of the INCOSE Systems Engineering Handbook, Generic Life Cycle Stages. Starting with Section 3.1, Introduction. Every man-made system has a life cycle, even if it is not formally defined. A life cycle can be determined as a series of stages through which something, a system or manufactured product, passes. In keeping with increased awareness of environmental issues, the life cycle for any system of interest must encompass not only the development, production, utilization, and support stages, but also provide early focus on the retirement stage when decommissioning and disposal of the system will occur. The needs for each of the subsequent stages must be considered during the earlier stages, especially during the concept and development stages, in order to make the appropriate trades and decisions to accommodate the needs of later stages in an affordable and effective manner. The role of the systems engineer encompasses the entire life cycle for the systems of interest. Systems engineers orchestrate the development of a solution from requirements definition through design, build, integration, verification, operations, and ultimately system retirement by assuring that domain experts are properly involved, that all advantageous opportunities are pursued, and that all significant risks are identified and mitigated. The systems engineer works closely with the project manager in tailoring the generic lifecycle, including key decision gates to meet the needs of their specific project. Per ISO IEC IEEE 15288, life cycles vary according to the nature, purpose, use, and prevailing circumstances of the system. The purpose in defining the system life cycle is to establish a framework for meeting the stakeholders' needs in an orderly and efficient manner for the whole life cycle. This is usually done by defining life cycle stages and using decision gates to determine readiness to move on from one stage to the next. Skipping stages and eliminating time-consuming decision gates can greatly increase the risks, cost, schedule, and performance, and may adversely affect the technical development as well by reducing the level of the systems engineering effort, as discussed in Section 2.8. Systems engineering tasks are usually concentrated at the beginning of the life cycle, but both industry and government organizations recognize the need for systems engineering throughout the system's lifespan, often to modify or change a system product or service after it enters production or is placed in operation. Consequently, systems engineering is an important part of all life cycle stages. During the utilization and support stages, for example, systems engineering executes performance analysis, interface monitoring, failure analysis, logistics analysis, tracking, management, etc. that is essential to the ongoing operation and support of the system. Section 3.2. Life cycle characteristics. 3 aspects of the life cycle. Every system life cycle consists of multiple aspects, including the business aspect, the business case, the budget aspect, funding, and the technical aspect, the product. The systems engineer creates technical solutions that are consistent with the business case and the funding constraints. System integrity requires that these 3 aspects are in balance and given equal emphasis at all decision gate reviews. For example, when Motorola's Iridium project started in the late 1980s, the concept of satellite-based mobile phones was a breakthrough and would clearly capture a significant market share. Over the next dozen years, the technical reviews ensured a highly successful technical solution. In fact, in the first decade of the 21st century, the Iridium project is proving to be a good business venture for all except for the original team who had to sell all the assets, at about 2% of their investment, through the bankruptcy court. The original team lost sight of the competition and changing consumer patterns that substantially altered their original business case. Figure 3.1 highlights 2 critical parameters that engineers sometimes lose sight of. Time to break even, indicated by the circle, and return on investment, indicated by the lower curve. I'm going to go down to the figure here. Figure 3.1 is the generic business life cycle from Stower, 2005, reprinted with permission from Heinz Stower. You can see here all the different aspects. So you got the different design cycle stuff, like the concept stage, the development stage, production stage, and utilization stage. The order intake goes up over time, and you can see here that originally the costs are outweigh all of the income, and then at about 9 or so years into this product's life cycle, they hit the break-even point. They would have hit the break-even point if for this example up here, but they had that too far out in the future, I assume, and so they never actually got a return on investment, a positive return on investment. Excuse me. Section 3.2.2, Decision Gates. Decision gates, also known as control gates, are often called milestones or reviews. A decision gate is an approval event in the project cycle, sufficiently important to be defined and included in the schedule by the project manager, executive management, or the customer. Entry and exit criteria are established for each gate at the time they are included into the project management baseline. Decision gates ensure that new activities are not pursued until the previously scheduled activities on which new activities depend are satisfactorily completed and placed under configuration control. Proceeding beyond the decision gate before the project is ready entails risk. The project manager may decide to accept that risk, as is done, for instance, with long lead item procurement. All decision gates are both reviews and milestones. However, not all reviews and milestones are decision gates. Decision gates address the following questions. Does the project deliverable still satisfy the business case? Is it affordable? Can it be delivered when needed? Decision gates represent major decision points in the system lifecycle. The primary objectives of decision gates are to ensure that the elaboration of the business and technical baselines are acceptable and will lead to satisfactory verification and validation. Ensure that the next step is achievable and the risk of proceeding is acceptable. Continue to foster business and seller teamwork, buyer and seller teamwork. Synchronize project activities. There are at least 2 decision gates in any project: authority to proceed and final acceptance of the project deliverable. The project team needs to decide which life cycle stages are appropriate for their project and which decision gates beyond the basic 2 are needed. Each decision gate must have a beneficial purpose. Pro forma reviews waste everyone's time. Even in Agile development, section 9.9, frequent interaction with stakeholders may minimize, but not eliminate, the need for decision gates. The consequences of conducting a superficial review, omitting a critical discipline, or skipping a decision gate are usually long-term and costly. The project business case issues of market demand, affordability, and realistic schedules are important decision criteria influencing concept selection, and they should be updated and evaluated at every decision gate. Inadequate checks along the way can set up subsequent failures, usually a major factor in cost overruns and delays. At each gate, the decision options are typically similar to the following. Acceptable. Proceed with the next stage of the project. Acceptable with reservations. Proceed and respond to action items. Unacceptable. Do not proceed, continue the stage, and repeat the review when ready. Unacceptable. Return to a preceding stage. Unacceptable. Put a hold on project activity. And unsalvageable. Terminate the project. Decision gate descriptions should identify the purpose and scope of the decision gate, entry and exit criteria, and host and chairperson. Should also describe attendees, location, the agenda and how the decision gate is to be conducted, evidence to be evaluated, actions resulting from the decision gate, method of method of closing the review, including timing for resolution of open action items, Decision gate approval follows review by qualified experts and involved stakeholders and is based on hard evidence of compliance to the criteria of the review. Balancing the formality and frequency of decision gates is seen as critical success factor for all systems engineering success areas. On large or lengthy projects, decisions and their rationale are maintained using an information management process. Upon successful completion of a decision gate, some artifacts, example, documents, models, or other products of a project lifecycle stage, have been approved as the basis upon future work must build. These artifacts are placed under configuration management. Section 3.3, Lifecycle Stages. ISO IEC IEEE 15288 states, a system progresses through its lifecycle as the result of actions performed and managed by people in organizations using processes for execution of these actions. A system progresses through a common set of lifecycle stages where it is conceived, developed, produced, utilized, supported, and retired. The lifecycle model is the framework that helps ensure that the system meets its required functionality throughout its life. For example, to provide system requirements and provide system solutions during the concept stage and development stage. Experts from other stages are needed to perform trade-off analysis, help make decisions, and arrive at a balanced solution. This ensures that a system has the necessary attributes as early as possible. It is also essential to have the enabling systems available to perform required stage functions. Table 3.1 lists 6 generic lifecycle stages. The purpose of each is briefly identified, and the options from decision gate events are indicated. Note that stages can overlap, and the utilization and support stages run in parallel. Note also that the outcome possibilities for decision gates are the same for all decision gates. Although the stages in Table 3.1 are listed as independent, non-overlapping, and serial, the activities constituting these stages can be in practice interdependent, overlapping, and concurrent. Up here is Table 3.1, the generic lifecycle stages, their purposes, and decision gate options. The lifecycle stages are as follows. They are concept, development, production, utilization, support, and retirement. If you wish to read over the purpose, feel free to pause the video and read them. And then for each of the decision options, each of the lifecycle stages, the various decision options are given over here. Excuse me. Consequently, okay, so I'll start back from up here actually. Although the stages in Table 3.1 are listed as independent, non-overlapping, and serial, the activities constituting these stages can, in practice, be independent, overlapping, and concurrent. Consequently, a discussion of system lifecycle stages does not imply that the project should follow a predetermined set of activities or processes unless they add value towards achieving the final goal. Serial time progression is not inherently a part of the lifecycle model. Stages do not necessarily occur serially, one after another in time sequence. One possible example of the progression of a system through its lifecycle is shown in Figure 3.2. When, in this handbook, reference is made to an earlier, prior, next, subsequent, or later stage, this type of model must be kept in mind to avoid confusion by inferring serial time sequencing. Subsequent chapters of this handbook will define processes and activities to meet the objectives of these lifecycle stages. Because of the iterative nature of systems engineering, specific processes are not aligned to individual lifecycle stages. Rather, the entire set of systems engineering processes is considered and applied at each stage of lifecycle development as appropriate to the scope and complexity of the project. Figure 3.3 compares the generic lifecycle stages to other lifecycle viewpoints. For example, the concept stage is aligned with the study period for commercial projects and with the pre-system acquisition and the project planning period in the U.S. Departments of Defense and Energy, respectively. Typical decision gates are presented in the bottom line. And then up here in Figure 3.2 that shows that the different life cycle stages are not necessarily in sequence. Shown down here is figure 3.3. It's pretty large, it kind of takes up the whole page, but it's comparisons of different life cycle models. So you get the generic one from ISO, IEC, IEEE, with the concept stage, development stage, production stage, then utilization and support at the same time, and then finally retirement. And then you've got all these other ones. You've got typical high-tech commercial systems, typical high-tech commercial manufacturer, US DoD, National Aeronautics and Space Administration, otherwise NASA, and the US Department of Energy. And then diving into the actual life cycle stages. Starting out, we have the concept stage, section 3.3.1. The concept stage begins with some recognition of a need for new or modified system of interest. Many industries employ an exploratory research activity in the concept stage to study new ideas or enabling technologies and capabilities, which then mature into the initiation of a new project for the system of interest. A great deal of creative systems engineering is done in this stage, and the systems engineer leading these studies is likely to follow a new idea into the concept selection, perhaps as a project champion. Often, the exploratory research activity identifies the enabling technologies. If the work is done properly in early stages of the life cycle, it is possible to avoid recalls and rework in later stages. Many life cycle models show the process beginning with requirements or user requirements. In fact, the process begins earlier with interactions and studies to understand potential new organizational capabilities, opportunities, or stakeholder needs. It is critical that in these early studies, a high-level preliminary concept be created and explored to whatever depth is necessary to identify technological risks and to assess the technology readiness level, the TRL, of the project. The focus is on studying potential technologies and determining the state of what is possible and what is not. In some instances, the project may be an outgrowth of research activities where the research engineer or scientist has no connection to a user-supported need. The preliminary concept and enabling technologies need to be identified early, and issues arising from the studies need to be addressed during the development stage, according to the National Research Council of the U.S. National Academies. One of the challenges in developing alternative concepts is that we often build on what has worked well for us in the past, without considering true alternatives, and thereby miss opportunities to make dramatic improvements. This problem has been widely recognized. The preliminary concept will also be used to generate early cost and schedule projections for the project if it moves ahead. Key activities during exploratory research are to clearly define the problem space, characterize the solution space, identify business or mission requirements and stakeholder needs, and, while avoiding any design work, provide an estimate of the cost and schedule for the full-scale development. Incomplete systems engineering in this stage can lead to poor cost and schedule projections, as well as poor understanding of technical alternatives, resulting in poor trades among the alternatives. For example, the Mars Science Laboratory rover, scheduled for launch in 2009, had to be delayed because of technical glitches. This resulted in missing the launch window, causing a 2-year delay and a 35% cost growth over the approved development cost. Program critics, however, claimed a 400% cost growth based on the early concept studies, and they threatened the project with cancellation as a result. The preliminary concept is a starting point, not an end point, as the project moves into the concept selection activity of the concept stage. The preliminary concept is not put under configuration control, and the key output from exploratory research is a clear understanding of the business and mission requirements and the stakeholder needs, an assessment of the technology's readiness to move to the next stage, and a rough estimate of the project costs and schedule requirements and technical feasibility to first article delivery. Concept selection is the second activity of the concept stage. The concept selection activity is a refinement and broadening of the studies, experiments, and engineering models pursued during the exploratory research activity. The first step is to identify, clarify, and document the stakeholders' conceptual operation of the system across the different stages of use and the environments it is to be used in. The operational concept, OPSCON, effort, should be undertaken to include any changes caused by the changes in the manufacture processes or materials, changes in interface standards, or new feature enhancements being added that can drive various aspects of concept selection of the system. During the concept stage, the team begins in-depth studies that evaluate multiple candidate concepts and eventually provide a substantiated justification for the system concept that is selected. As part of this evaluation, mock-ups may be built for hardware or coded for software. Engineering models and simulations may be executed, and prototypes of critical elements may be built and tested. Engineering models and prototypes of critical elements are essential to verify the feasibility of concepts, to aid the understanding of stakeholder needs, to explore architectural trade-offs, and to explore risks and opportunities. These studies expand the risk and opportunity evaluation to include affordability assessment, environmental impact, failure modes, hazard analysis, technical obsolescence, and system disposal. Issues related to integration and verification must also be explored for each alternative system concept, since these can be discriminators in system selection. The systems engineer facilitates these analyses by coordinating the activities of engineers from many disciplines. Key objectives are to provide confidence that the business case is sound and the proposed solutions are achievable. The concept stage may include system and key system element level concept and architecture definition and integration, verification, and validation planning. Early validation efforts align requirements with stakeholder expectations. The system capabilities specified by the stakeholders will be met by the combination of system elements. Problems identified for individual system element level concepts should be addressed early to minimize the risk that they fall short of their required functionality or performance when the elements are finally designed and verified. Many projects are driven by eager project champions who want to get on with it. They succumb to the temptation to cut short the concept stage, and they use exaggerated projections to support starting development without adequate understanding of the challenges involved, as comically illustrated in Figure 3.4. Many commissions reviewing failed systems after the fact have identified insufficient or superficial study in the concept stage as a root cause of failure. Up here is Figure 3.4. It's a Dilbert comic. It says the importance of the concept stage from 1997 by Dilbert. It says, "Wally, we don't have time to gather the product requirements ahead of time. I want you to start designing the product anyway. Otherwise, it'll look like we're not accomplishing anything." And then at the end, it says, of all my projects, I like the Doom ones best. So, he knows it's not going to work. The next lifecycle stage is the development stage. The development stage defines and realizes a system of interest that meets its stakeholder requirements and can be produced, utilized, supported, and retired. The development stage begins with the outputs of the concept stage. The primary output of this stage is the system of interest. The outputs can include a system of interest prototype, enabling system requirements, or the enabling systems themselves, systems documentation, and cost estimates for future stages. Business and mission needs, along with stakeholder requirements, are refined into system requirements. These requirements are used to create a system architecture and design. The concept from the previous stage is refined to ensure all system and stakeholder requirements are satisfied. Requirements for production, training, and support facilities are defined. Enabling systems requirements and constraints are considered and incorporated into the design. System analyses are performed to achieve system balance and to optimize the key for design parameters. One of the key activities of the development stage is to specify, analyze, architect, and design the system so that the system elements and their interfaces are understood and specified. Hardware and software elements are fabricated and coded. Operator interfaces are specified, tested, and evaluated during the development stage. Operator and maintainer procedures and training are developed and delivered to ensure humans can interface with the system of interest. Feedback is obtained from both external and internal stakeholders through a series of technical reviews and decision gates. Projects that are not showing acceptable progress may be redirected or even terminated. The development stage includes detailed planning and execution of the IV&V activities. The planning for these activities needs to take place early to ensure that adequate facilities and other resources are available when needed. A source of additional information about IV&V and its significance for project cost and risk when those activities are optimized was the subject of the European Union SIS test program. Section 3.3.3, the production stage. The production stage is where the system is produced or manufactured. Product modifications may be required to resolve production problems, to reduce production costs, or to enhance product or system capabilities. Any of these may influence system requirements and may require system re-verification or revalidation. All such changes require systems engineering assessment before changes are approved. Next up is the utilization stage. The utilization stage is where the system is operated in its intended environment to deliver its intended services. Product modifications are often planned for introduction throughout the operation of the system. Such upgrades enhance the capabilities of the system. These changes should be assessed by systems engineers to ensure smooth integration with the operational system. For large complex systems, midlife upgrades can be substantial endeavors requiring systems engineering effort equivalent to a major program. 3.5. Support. The support stage is where the system is provided services that enable continued operation. Modifications may be proposed to resolve supportability problems, to reduce operational costs, or to extend the life of the system. These changes require systems engineering assessment to avoid loss of system capabilities while under operation. And then finally, it's the retirement stage. Section 3.3.6. The retirement stage is where the system and its related services are removed from operation. Systems engineering activities in this stage are primarily focused on ensuring that the disposal requirements are satisfied. Planning for retirement is part of the system definition during the concept stage. Experience has repeatedly demonstrated that the consequences with system requirements is not considered from the outset. Early in the 21st century, many countries have changed their laws to hold a developer of a system of interest accountable for proper end-of-life disposal of the system. And the next section is section 3.4, life cycle approaches. Various life cycle models, such as the waterfall, the spiral, and the V, are useful in determining the start, stop, and process activities appropriate to the life cycle stages. Graphical representations of life cycle stages tend to be linear, but this hides the true incremental, iterative, and recursive nature of the underlying processes. The approaches that follow imply full freedom to choose a development model and are not restricted to sequential methods. 3.4.1 Iteration and Recursion. Too often, the system definition is viewed as a linear, sequential, single pass-through of the processes. However, valuable information and insight need to be exchanged between the processes in order to ensure a good system definition that effectively and efficiently meets the mission or business needs. The application of iteration and recursion to the lifecycle processes with the appropriate feedback loops helps to ensure communication that accounts for ongoing learning and decisions. This facilitates the incorporation of learning from further analysis and process application as the technical solution evolves. Figure 3.5 shows an illustration of iteration and recursion of the processes. Iteration is the repeated application and interaction between two or more processes at a given level in the system structure or hierarchy. Iteration is needed to accommodate stakeholder decisions and evolving understanding, account for architectural decisions and constraints, and resolve traits for affordability, adaptability, feasibility, resilience, etc. Although the figure only shows a subset of the life cycle technical processes, there can be iteration between any of the processes. For example, there is often iteration between system requirements definition and architecture definition. In this case, there is a concurrent application of the processes with iteration between them, with evolving system requirements help to shape the architecture through identified constraints and functional and quality requirements. The architecture trades, in turn, may identify requirements that are not feasible further driving requirements analysis with trades that change some requirements. Likewise, the design definition could identify the need to reconsider decisions in trades in the requirements definition or architecture definition process. Any of these can invoke additional application of the system analysis and decision management processes. Recursion is the repeated application of and interaction of processes at successive levels in the system structure. The technical processes are expected to be recursively applied for each successive level of the system structure until the level is reached where the design is made to make, buy, or reuse a system element. And during the recursive application of the processes, the outputs at one level become inputs for the next successive level. This figure here shows iteration and recursion. Section 3.4.2 Sequential Methods. On projects where it is necessary to coordinate large teams of people working in multiple companies, sequential approaches provide an underlying framework to provide discipline to the lifecycle processes. Sequential methods are characterized by a systematic approach that adheres to specified processes as the system moves through a series of representations from requirements through design to finished product. Specific attention is given to the completeness of documentation, traceability from requirements, and verification of each representation after the fact. The strengths of sequential methods are predictability, stability, repeatability, and high assurance. Process improvement focuses on increasing process capability through standardization, measurement, and control. These methods rely on the master plans to anchor their processes and provide project-wide communication. Historical data is usually carefully collected and maintained as inputs to future planning to make projections more accurate. Safety-critical products, such as the THERAC 25 medical equipment described in section 3.6.1, can only meet modern certification standards by following a thorough, documented set of plans and specifications. Such standards mandate strict adherence to process and specified documentation to achieve safety or security. However, unprecedented projects or projects with a high rate of unforeseeable change, poor predictability, and lack of stability often degrade, and a project may incur significant cost trying to keep documentation and plans up to date. The V model, introduced in Forsberg and Moose, described in Forsberg et al., and shown in Figure 3.6, is a sequential method used to visualize various key areas for SE focus, particularly during the concept and development stages. The V highlights the need for continuous validation with the stakeholders, the need to define verification plans during requirements development, and the importance of continuous risk and opportunity assessment. The V model provides a useful illustration of the SE activities during the lifecycle stages. In this version of the V model, time and system maturity proceed from the left to the right. The core of the V, i.e. those products that have been placed under configuration control, depicts the evolving baseline from stakeholder requirements agreement to identification of a system concept to the definition of elements that will comprise the final system. With time moving to the right, the evolving baseline defines the left side of the core of the V, as shown in the shaded portion of 3.7. We'll go ahead and show the V model. Important part of this diagram is the decomposition as you go downwards in the V, and then the integration and verification on the right side of the V. A key attribute of the V model is that the time and maturity move from left to right across the diagram, as shown in Figure 3.7. At any instant of time, the development team then can move their perspective only along the vertical arrow from the highest level of the system requirements down to the lowest level of detail. The off-core opportunity and risk management investigations going downward are just addressing development options to provide assurance that the baseline performance being considered can indeed be achieved, and to initiate alternative concept studies at the lower levels of detail to determine the best approach. These downward off-core investigations and development efforts are entirely under control of the development team. On the other hand, the essential upward off-core stakeholder discussions, the in-process validation, ensures that the proposed baselines are acceptable to management, customer, user, and other stakeholders. Changes to enhance system performance or to reduce risk or cost are welcome for consideration, but these must go through formal change control, since others outside the development team may be building on previously defined and released design decisions. The power of understanding the significance of the off-core studies is illustrated in a NASA JPL Jet Propulsion Laboratory report. As entities are implemented, verified, and integrated, the right side of the core of the V is executed. Figure 3.8 illustrates the evolving baseline as system elements are integrated and verified. Since one can never go backward in time, all iterations in the V are performed on the vertical time now line. Upward iterations involve the stakeholders and are the in-process validation activities that ensure that the proposed baselines are acceptable. The downward vertical iterations are the essential off-core opportunity and risk management investigations and actions. In each stage of the system lifecycle, the SC process iterates to ensure that a concept or design is feasible and that the stakeholders remain supportive of the solution as it evolves. Excuse me. Section 3.4.3 Incremental and Iterative Methods. Incremental and iterative development methods have been in use since the 1960s. They represent a practical and useful approach that allows a project to provide an initial capability followed by successive deliveries to reach the desired system of interest. The goal is to provide rapid value and responsiveness. The IID approach is used when the requirements are unclear from the beginning, or the stakeholder wishes to hold the system of interest open to the possibilities of inserting new technology. Based on an initial set of assumptions, a candidate system of interest is developed and then assessed to determine if it meets stakeholder needs or requirements. If not, another evolutionary round is initiated, and the process is repeated until a system is delivered to satisfied stakeholders or until the organization decides to terminate the effort. Most literature identifies or agrees that the IID methods are best applied to smaller, less complex systems, or to system elements. The focus is on flexibility and on allowing selected elements to be taken out of sequence when the risk is acceptable. Tailoring in this way highlights the core activities for product development. The features that distinguish IID from the sequential approaches are velocity and adaptability. While market strategies often emphasize that time to market or speed is critical, a more appropriate criterion is velocity, which considers direction in addition to speed. By incorporating the stakeholders into the working level teams, the project receives continuous feedback that they are going in a direction that satisfies the stakeholders' highest needs first. One downside is that reactive project management with a stakeholder that often changes direction can result in unstable, chaotic projects. On the one hand, this approach avoids the loss of large investments and faulty assumptions, but on the other hand, emphasis on a tactical viewpoint may generate short-term or localized solution optimizations. IIDs may also be plan-driven in nature when the requirements are known in the early life cycle, but the development or the functionality is performed incrementally to allow for the latest technology insertion or potential changes in needs or requirements. A specific IID methodology is called evolutionary development and is common in research and development environments. Figure 3.9 illustrates how this approach was used in the evolution of the tiles for the NASA Space Shuttle. An example of an incremental and iterative model is the incremental commitment spiral model. The ICSM builds on the strengths of current process models, such as early V&V concepts in the V model, concurrency concepts in the concurrent engineering model, lighter weight concepts in the agile and lean models, risk-driven concepts, and the spiral model, the phases and anchor points in the rational unified process, and recent extensions of the spiral model to address systems capability acquisition. A view of the ICSM is shown in Figure 310. In the ICSM, each increment addresses requirements and solutions concurrently rather than sequentially. ICSM also considers products and processes, hardware, software, and human factors aspects, and business cases of alternative product configurations or product line investments. The stakeholders consider the risk and risk mitigation plans and decide on a course of action. If the risks are acceptable and covered by risk mitigation plans, the project proceeds into the next spiral. Figure 3.11 presents another view of the ICSM. The top row of activities indicates that a number of system aspects are being currently engineered at an increasing level of understanding, definition, and development. Section 3.5. What is best for your organization, project, or team? Conway's law suggests that organizations which design systems are constrained to produce designs which are copies of the communication structures of those organizations. Systems thinking and systems engineering help organizations avoid the pitfall of Conway's law by ensuring that systems design is appropriate to the problem being addressed. And shown here is the IID and evolutionary development. Shown here is the incremental commitment spiral model. Shown here is Figure 3.11, the phased view of generic incremental commitment spiral model process from Bohm et al. It shows the ICSM anchor points, ICSM lifecycle phases, activities, concurrent risk and opportunity driven growth of system understanding definition, the evaluation of evidence of feasibility to proceed, and stakeholder review and commitment. One of the earliest books on systems engineering management identified 3 simple criteria for such organizations: facilitate communications, streamline controls, and simplify paperwork. The way to effective systems engineering management is not in the direction of formal, formidable, massive documentation. It does, however, reside in the direction of creating a total environment which is conducive to the emergence and effective utilization of creative and inventive talents, oriented towards achieving a system approach with a minimum of management encumbrances. Whenever someone, be it an individual or a company, wants to reach a desired end, they must perform a series of actions or operations. Further, they must consider the order of those operations, their dependencies, who will perform them, what they require, and what they will generate, how long it will take to complete them, and what tools they will employ. Thus, individuals and organizations follow processes, be they predefined or ad hoc. Because process components, activities, products, agents, tools, and their interactions, information flow, artifacts flow, control, communications, timing, dependencies, and contingency, can vary, the processes will differ, even if the performing organizations have the same level, scope, and goal. So why should an organization care about the process? In short, this is to better understand, evaluate, control, learn, communicate, improve, predict, and certify the work performed. For a given organizational level, the processes vary with the project's goals and available resources. At a high level, the company's business strategy determines the business approach with the main goals of profitability, time to market, minimum cost, higher quality, and customer satisfaction setting the priorities. Similarly, the company size, the number of knowledge and experience of people, both engineers and support personnel, and hardware resources determine how to achieve those goals. The application domain and the corresponding system requirements, together with the constraints, form another important factor in defining and applying processes. So what really is best for my organization? The answer is that it really depends on the situation. Depending on the perspective, different processes are defined for entire organizations, teams, or individuals. A one-size-fits-all approach does not work when defining processes. Thus, organizations must continuously document, define, measure, analyze, assess, compare, and change processes to best meet project goals. One would hardly expect to find the same processes used in a startup e-commerce company as in NASA. The intended goal shapes the process in terms of scope, namely the stages and activities covered at an organizational level. In any case, the selected processes should help guide people on what to do, how to divide and coordinate the work, and ensure effective communication. Coordination and communication, for example, form the main problems in large projects involving many people, especially in distributed projects where people cannot communicate face to face. I'm going to check how long these case studies are before I read them. I might put them as a separate recording. I'll upload that as a separate recording. Alright, thank you for watching. Hope you got something out of it.